Okay, we should be
Congrats.
live right now.
Greetings.
Hello, world.
Hello, world. In theory, but we need people to say that they see us. We're like one of that quantum thing. We
We're
don't
both
exist.
live and not live.
We don't exist until somebody makes an observation of us.
Ah,
All right, so as we were preparing for this, I was just sort of scrolling through the news, and I have to say I think we've come full circle in the world now that I've seen a Lego set based on a Minecraft world. It's just
what?
kids are going to find out
Yeah.
that Legos are cool again.
Yeah, yeah.
When were Legos not cool?
Wasn't there a movie that said Legos were cool?
There's also a
Everything's
movie
awesome.
about
It
emojis,
was
and so
awesome.
the world's
Yeah.
also going to hell.
Yeah,
But,
that is true.
Damn you kids, get off my lawn, says Morgan, who's actually a 5-year-old man.
All right. Apparently, we have been observed, but you can't measure both our momentum. Anyway, I'm going to say hi to a bunch of people. Here we go. Hello to Adam Synergy, Arnold Post, Ben Ofa, Baruch Klankar, Carolyn B, Treg Kahar, Connor Lennon, Ilid Avron, Eric Charlin, Eric Bennett, Galaxia, Giselle Sabarin, Graham Walbridge, Guido Bibra, Hammond Wasim, High Champ 1, John Gallant, John Seffield, John Victor, Johnny Zed, Kenneth Lepre, Kimberly Cartiers are here with us, Larry Beckham, Linda Sadek, Lucinda Rideout, Malcolm Bond, Morgan Renberg, Nancy Graziano, Peter Quinn, Philip Berthus, Peter Klimko, Psilocybin Logician, Recon Wu, there we go, Raza Siddiqui, winner of last week's book, congratulations, Rick Schwartz, Seth Cooper, Stephen Hawkins, and Tom Van Scotter. Hey, everybody. Yeah, so, man, a huge apologies last week. So I was at Brian Brushwood's house and using his studio. And he's got a fantastic studio. He's got an amazing setup. He's got just like, it's like, driving someone's Lamborghini, but he had to go. And so I did the best that I could using this Lamborghini of a studio, not an actual Lamborghini. He drives a Jeep. But anyway, so I was trying to use this Lamborghini of a studio, and like I couldn't even make sound go into my headphones, even though I'm sure it had 17 ways to do it, and you could control all these knobs to really. Anyway. Okay.
Too fancy.
It was too fancy. Yeah, that was the problem, is that it was too fancy. I needed something that was less fancy. So
Fewer buttons.
fewer buttons. What else is happening?
Morgan got a PhD. Kimberly got a PhD.
We're going to talk about that in the show, so we're going to make a big fuss about that in a second. So don't you worry.
Sandy passed her qualifying exam, so it's success all around.
Ooh,
Nice.
What is she qualified to do?
get a PhD.
Well, now that she's qualified to be an astronomer, she's qualified to do absolutely nothing.
Oh,
Morgan Renberg. You
I'm
shut
gonna
your
stick a
mouth.
cat on you, Morgan,
yeah,
for that.
yeah.
You're lucky you're in Colorado. I'd smack you.
Truth hurts sometimes.
Oh, astronomers.
We're the best. We're on top of the world.
Is there like
I'm
some
a
kind of
planetary scientist, thank you.
is there like an astrophysicist versus astronomer versus
Oh yeah. I mean, so like
cosmologist?
planetary scientists, we know we're like not as arrogant as the astronomers. The astronomers know they're not as arrogant as the astrophysicists.
And
then
the
everyone is
astrophysicists
just
are
like
not as arrogant as cosmologists.
Yeah, cosmologists, and then the physicists are the most arrogant. But yeah, like who cares about string theory? I mean, I guess some people do.
I'm gonna start this show before this gets ugly, and then we will clip this.
Food fight.
Glad this won't make it to the permanent version.
Yeah, and we'll slice it out, and there we go. All right, I'm gonna get this set up, and we'll begin. All right. Sherrick wants to know if I've got my play button. I have not gotten my play button yet. It's still, I don't know, coming. Okay. I think I'm ready. It's 12:05. Let's do it. Hello, everyone, and welcome to the Weekly Space Hangout for Friday, I'm gonna do it again. I'm gonna do this again because I can. It's May.
It's gonna be May.
Yeah.
Yeah, if
It
it was
doesn't
April,
feel
I
like
still
May.
think
That's my
it's
problem. Is that it
intensity
doesn't
again.
feel like May here.
Someone's
Still
been
April.
sitting around astronomers too long, losing life skills.
Cut it right there. All right.
I'm gonna hurt you one day.
Hello, everyone, and welcome to the Weekly Space Hangout for Friday, May 19th, 2017. I'm Fraser, Cain, publisher of Universe Today. This week, we're going to be talking about massive black hole formation, discovery of a moon around a dwarf planet that still doesn't even have a name, trouble for the SLS, a Neptune-sized planet that looks like Jupiter, and how the rivers on Titan are more like Mars than they are for Earth. So joining me this week, and we got a sort of a special intro today, we've got Dr. Kimberly Cartier.
Hello. I've survived.
You did. So when did it actually come together?
So my defense was May 9th. And it was 3 hours long,
Oh my
over
God.
3 hours long. It was horrifying. Well, I had 6 people, so that makes sense. I passed, and then my body promptly shut down for a week, and now I'm recovered.
Well, congratulations. And so,
Thank you.
like, what's your specific title now? If we were to,
Dr. Kimberly Cartier,
and then the rest of it?
PhD.
But is there
Yeah.
like, it's like some
Oh.
kind of more specific title?
I don't know what you mean.
Like of astronomy,
Professor of
Oh.
astronomy.
astrophysics.
Yeah,
Oh, of astronomy and astrophysics, I suppose.
right on.
Both astronomy and astrophysics.
But we have not one but two new doctors today. Morgan Renberg, Dr. Morgan Renberg.
Hey, Fraser. It's good to be back. It's been like a month.
Yeah, I know. And so we have, I guess about a month ago, sort of explained to everyone what happened. When did it happen? When
Yeah,
did it
so
go
I
down?
defended 2 weeks ago yesterday, and then promptly had to become an adult so that I could, go buy a car and find a place to live and go get a job and all that stuff that I've been plugging my ears for the last 5 years.
And so your official then description?
My degree is in astrophysics and planetary science,
Ooh.
so I can throw shade, I guess, in both directions.
Both directions. Right on. And we got Sandy Springman, who is now on track to get her PhD.
Yay!
Wow.
I am now a doctoral candidate.
Sandy had the hardest job of any of us.
Oh my God. One of my committee members, we won't name names, fell asleep.
Oh my God, that's horrible.
And he woke up while we were discussing deuterium hydrogen ratios in comets.
Yeah.
And he's like, we're talking about this in comets, or what are we talking about? Hydrogen, deuterium? He's just like, go back to bed.
So, how will, if all goes well, what will that mean for you?
I will eventually have a PhD in planetary sciences around 2019 or 2020.
Excellent.
Just in time for SLS.
Or no, she'll probably beat SLS.
I'm gonna beat LSST, I think.
Oh, really? Okay.
Yeah, you are.
And this is round 2 for me.
All right, and we've got a special guest this week as well. So let's get into that part of it. Let's get all the info here in front of me. All right. So Eric Fisher, you come from Labfundr. Welcome
Hi,
to the Weekly
yes.
Space Hangout.
Thank you. Thanks for having me.
So before we get into the full show, I just want to remind everyone, big thanks to the Weekly Space Hangout crew. Those are, of course, the people who organize all the behind-the-scenes information. They run this chat down here. So if you want to join this chat and this really great community, really they're the producers of this show, go to wshcrew.space and they can hook you up. All right. Let's get on with it. All right. So Eric, what is Labfundr?
Labfundr is a crowdfunding platform for science specifically. So I did my PhD in biochemistry and molecular biology. I think so many PhDs have 2 names. Kind of funny. So I did that in Halifax, Nova Scotia, Canada. And then during that time, I was really just seeing the funding gaps that were really harming, particularly young scientists' careers and their ability to get off the ground, make discoveries and publish. And then at the same time saw that there's really no home in the crowdfunding world for researchers in Canada, and kind of, the light bulb went on, and that was kind of the birth of the idea to create Labfundr. So that was a little while ago, and now that's led to where we are today, and we're about to launch our first campaign next Tuesday. So yeah.
Now we're both Canadians. So where about are you in the country?
I'm just over in Halifax, so just a couple time zones away.
Yeah, we're on opposite sides, on opposite coasts of
right.
our country. So,
Yeah.
I mean, I've really seen that this idea of crowdfunding science, it feels like it kind of came out of. It was quite a surprise to me. I think everyone is so used to the way funding science has gone in the past, which is very much that it's been this government thing. It's been, the National Science Foundation here in Canada. There's the equivalent in the US, that the money goes into these science foundations through our taxes and then goes out to these different people. And we apply for grants, and the information is trickled out that way. And yet, I think one of the big surprises for me, and someone who works in this, is just the amount of kind of grassroots interest in helping participate and help make the science happen. So can you let me know sort of, what is the state of kind of crowdfunding for science, both with what you do and just across the world?
I think it's early days. I mean, there's been some great platforms elsewhere in the world, like in the States, there's experiment.com, and there's, in the UK and Europe and other places, there's been hundreds of campaigns for science crowdfunding, but it's still, minority of scientists sort of getting into this, as you say, totally new mechanism of funding research. And I think that, you're bang on in terms of getting people to really connect with researchers. And it's about, bringing researchers and the general public kind of closer together, and kind of chatting more about science and getting out of the ivory tower. And, that's what gets me excited more so. Like, the funding is obviously, a must-have for a lot of research to happen, but to really connect and help people feel, I guess, like, kind of like part of the team, and really kind of get excited about the process of science, not just the end product. And crowdfunding is just a perfect kind of mechanism to keep people kind of looped in as things are unfolding.
So can you give me some examples of projects that are on the platform right now?
No, no, we're brand new.
Yeah.
We've got a lot of cool projects in the works. So our first one launching next week, I can't give you an example of it because they're just about ready to go. It's called the Caliper Project, and that's it's a children's health study. So they take blood samples from healthy children, and they've created a database so that potentially sick kids who get blood tests can get more accurate test result interpretations. Because right now, and I didn't know this till started chatting with them, if you're a kid and you get a blood test, your results are compared to healthy adult values a lot of the time, and that there's a lot of inaccuracies that can happen because of that. So that's something that can have immediate clinical impact, and plus this is an ongoing study, and they've published I think about 40 papers, and the data's really helping push research forward as well. So that's a pretty cool project, and we're thrilled to help them out. And we've been talking to people who are doing bioengineering, people doing research on autism, space research. So it's we're really excited to roll out some pretty cool stuff over the coming months.
One of the risks, I think, is people funding projects that are kind of, I don't know, like, it's like researching animals, right? People want to fund research of panda bears and not research tapeworms. you
Yeah,
know,
yeah.
that the sort of the sexier the subject, the more easy it is to raise money. So how do you
Yeah.
think this crowdfunding, what's it going to be good at, and what things do you think maybe it's not going to be so good for?
That's a really a great point, and I think that in the beginning, I was, I guess, aware of the like that possibility of it being a popularity contest, sort of the cute and fuzzy stuff of the world winning out. But there's been enough science crowdfunding that there's actually been research on science crowdfunding, and they actually so some folks published a paper about, I think it's about across 370 odd campaigns. They actually found that the field of research didn't impact the probability of success for the campaigns, which was, I think, very encouraging, because across all scientific fields, people were able to succeed in raising money, or if they did or didn't succeed, it wasn't what they were studying that impacted that. So I think it's more about how you tell the story about what you're doing, and how clear and concise you are about what's the goal of the project, and it really, how well you connect with potential donors or contributors. I think that goes a long way, and your own network of people ahead of time. You have an audience on social media, things like that. So I think the popularity contest thing won't play quite as big a role as I might have thought in the beginning.
Do you think that there is a chance that I guess direct funding of research will start to sort of not necessarily overtake, but provide a significant amount of research budget compared to, I mean, I'm sure this is what you've bet your, you've sort of bet your future on this, but where do you see this playing out over the future? Are we going to see a lot of stuff funded?
That's a good question too. And I think there, like, in terms of setting expectations, like, really we're talking about, the thousands to maybe the tens of thousands of dollars range, where, is what people can aim for in terms of science crowdfunding. And obviously operating grants are, six figures, pretty big. I do think it'll grow as this awareness of crowdfunding continues to grow. It's still sort of expanding. It's not really totally mainstream yet. And a lot of people in the broader fundraising world look at crowdfunding as a really great way to, because they sort of challenge for them is to show what the impact is, and to really connect more with donors. So crowdfunding is going to keep getting more and more mainstream. And I think you'll see it kind of merge with other fundraising sort of techniques and stuff. So I do think that bar will kind of go up, especially if it's something that excites us is the possibility of dollar matching campaigns, where there could be a big lump sum from a person or a group, and the crowd could come on and donate alongside that, and that would sort of double or triple what the crowd might have given otherwise. So yeah, but in the near term, I do think that it's more about filling funding gaps, helping do pilot studies, get preliminary data to make a grant application stronger, for example, or maybe someone runs out of funds right at the finish line and needs to get some bridge funding, or something we're excited about too is the campaign category of to support conference travel or training, and that's a bit of money that can make a huge impact on someone's career, right? It's not massive operating grant, but it's something that could really help a young researcher, in the early critical days. So that's where we're at.
Yeah. I mean, I think mentioned some of those parts of, like, some kind of preliminary research, things like that. Like, I think that there are. I know that there are people doing research into things like psilocybin, right, and the effects of that as potential for various mental health issues. And there's stuff that's maybe on the fringes, or maybe stuff that people they have a personal interest in having that research be done, and instead of trying to just nag their government officials and go through that entire process to shortcut it and go, hey, well, let's just gather together all of the money to do some kind of preliminary research, see if it's interesting, and then take that to a funding agency and try to take the research to the next level.
Yeah, for sure. And I think actually there's just the Naylor report just came out, which is a huge kind of analysis of science in Canada. And a lot of the things really struck a chord with me in terms of, some multidisciplinary projects nowadays have a really hard time in peer review because they just don't fall in the right bucket. So there's stuff like that. And there's, stuff that's maybe a little out there. It just doesn't match the existing sort of categories. And it's, cutting edge stuff that's, from a reputable, researcher. But, the field has advanced faster than maybe the bureaucracy behind it.
Yeah. So can you give us an idea, like, you've given us an idea on what one project that's going forward shortly. What is the sort of amount of money that you figure a lot of these projects are going to require? How much funds should they be trying to raise?
I think we're looking at what's gone on in other countries. Sort of the average, I would say, 5,000 would be pretty much the ballpark, and then and it depends on the size of your network and sort of if you've got other funding that you could make a matching funds type of campaign. But yeah, I would say 5,000 and maybe 10 or above if you've really got something that you can really get a lot of people rallying behind. But I think that it's good to set a tangible, reachable goal, but it's also really good to have those sort of next goals in mind. Like if you hit that goal, be able to switch gears and tell people what you could do with the next amount of money, or like kind of have those stretch goals, as they're called, in mind.
Yeah. I mean, I've always been, people probably know that I worked with HeroX for a while. I'm a gigantic fan of just the sort of crowdfunding in general. And I even think, just an analogy, I think, I'm wearing my Twitch t-shirt right now.
Yeah, nice.
That Twitch is a good example of a thing that people, like, no one knew that people wanted to watch video games, and nobody knew that people wanted to watch other people play video games more than they want to watch television. Like right now, Twitch has more people watching it live than I think Netflix, Hulu, all of these other streaming services, simultaneously. Yeah. And so it's like this, it's mind-bending. Same with YouTube. YouTube gets more traffic than all of the other networks combined. Like, what do you know? People want to see this kind of thing, or cat videos, or people play Minecraft, whatever. And my feeling is that there are these surprises where human behavior, we have never had this opportunity to directly contribute to these kinds of projects. And now suddenly all these really interesting services are popping up. Patreon is one, that helps fund the work that I do with Universe Today. What you guys doing and some of the other crowdfunding, Kickstarter, et cetera, et cetera, et cetera. And now we're starting to see if there are successes, there could be some positive feedback loop where you're like, well, instead of going through this indirectly through the government and trying to vote and trying to, convince politicians that climate change is a real thing, you just, if you believe in it, give $100 and the research gets done and human science pushes forward. So I think it's I really think it's a very interesting and very exciting thing. And I think you're exactly right. We are in the early days of this.
Yeah, for sure. And I love to hear what you're saying. Yeah, because I really think that, some science is well funded, other stuff is really struggling. And, I don't think that there's ever a reason to be satisfied with the status quo, right? We can inspire people to feel empowered to actually make a difference themselves. And that's what I think the power is with this, in terms of getting people to rally behind, maybe it's climate science, maybe it's a rare disease that gets neglected. by drug companies. Who knows? And I think that it's just a really mechanism, like the way to connect people and bring the public into the research world, and that's something we want to encourage and are working with the campaign creators to really as a give back to provide that transparency and to make it fun too, like not to send out sort of huge sort of blocks of results and text and stuff, but just send out quick photos or clips. Someone even joked about a researcher wearing a GoPro. I don't know if that'll happen, but like just sort of cool things to sort of bring people into the research world in a meaningful way.
Eric, thank you so much for joining us today. Now, we've seen the website. Where else can people find out more?
So the website for sure. We're on Facebook with our Labfundr page and Twitter. Putting some stuff on Instagram as well. So yeah, definitely. And if you're interested in staying up to date, for sure, go to labfundr.ca and sign up to our newsletter. And we've got a lot of cool stuff coming up. So
wonderful.
Yeah, stay tuned.
All right. Well, Eric, thank you so much for joining us on the Weekly Space Hangout, and good luck. And as soon as you get something astronomy, space related, let me know, and I'll help you guys get the word out.
Absolutely. Yeah, that sounds great.
You see, in your background, you've got an aurora there. So let's get that done.
Yeah.
All right.
Yeah, exactly.
Let's figure out what that is.
Yeah. Do some science on it.
Yeah, that'd be great. All right. Thanks for joining us.
Have a great weekend. Thanks, guys.
All right, let's get on with the rest of the show, all the topics. Once again, if you want to ask some questions, this is a place to do it. Just go to wshcrew.space. You can also post some questions into the chat, and if I have time, we will try to sneak them in and ask people. Now we get to follow Fraser's whim. What do I want to learn about first? Morgan, I want to hear what's gone wrong with the Space Launch System.
So we've been talking a lot for years now about the Space Launch System, and nothing that happened this week is sort of imperiling continued progress on it. It's more an accounting of the trouble that it's been facing along the way. And this comes in two parts. And the first was a request made earlier this year by the Trump administration for NASA to evaluate whether the first launch of SLS with the Orion capsule on top could include humans. It was originally intended that this would be an uncrewed launch just to test the entire system, send the capsule out around the moon and back to the Earth. And then they'd put humans on a secondary launch that would occur sometime after that. And so NASA followed this directive and analyzed what it would take to put a crew on that very first mission. And they found it would cost somewhere between $600 and $900 million. And a lot of this was because many pieces of the life support system aren't expected to be ready until, say, 2021 or even beyond that. And this just kind of highlights the schedule problems that SLS has been facing, because the original launch for SLS was supposed to be by the end of the year in 2015. Now that's 2 years past from us, and they're looking at this first launch to be now the end of the year in 2018, with the possibility of slipping that even farther. And because of this $600 to $900 million surcharge to put astronauts on this first flight for something that really wouldn't be necessary, NASA has told the president that this is not a course of action that they recommend. And I think the expectation is that the White House will follow that course of action, and we'll see a first crew on SLS coming in the 2020s. And the second part of this story was a report from NASA's Inspector General. And the Inspector General is basically the internal oversight that every federal agency has, making sure that they're following their mandate, they're spending their money correctly, they're allocating other resources in a sensible way. And this report highlighted trouble with the testing of the giant fuel tanks about half the size of a football field or a soccer pitch. And they need these enormous stands to be built to sort of fill them up, test them, and make sure that they're working. And NASA elected to build these test centers at the Marshall Space Flight Center, instead of building them where all the other rocket testing is done at this Stennis Space Center. And the reason that this is notable is that the Stennis Space Center is just 40 miles away from where these tanks are being built. And the Marshall Space Flight Center is 1,240 miles away on a journey by barge. So rather than just sort of driving them across the border from Louisiana into Georgia to test them at Stennis, they put them on a barge through the Gulf of Mexico, up through some of the major rivers in the U.S., and it takes weeks to get them there. And that, of course, is very expensive. It costs about $500,000 just to send one of these fuel tank segments up the river to Marshall. And that's more than twice as much as it costs to stick it on a truck, drive it 40 miles into Stennis. And when the Inspector General looked back, they could find no sort of justification for why this had been done. Both NASA centers had submitted proposals for building the test systems there, but NASA had seemingly chosen the Marshall plan without ever sort of looking at the other plan and deciding whether or not it was more or less cost efficient. And the sort of accusation that's being implied here is that this is just a continuation of the idea that SLS is a jobs program more than it is a space technology program.
Yeah, and we've definitely talked about that in the past, that that a big part of the SLS was to put the space shuttle workforce, to continue them working instead of having to lay them all off.
Right, and the Marshall Space Flight Center is located in Alabama, which is home to sort of the core support in Congress for SLS, while support for the constituents at the other space centers is somewhat reduced. And the result of that is NASA may be spending tens of millions of dollars more simply to test these tanks 1,000 miles away because of sort of political pressure. And when you're talking about an effort as expensive as the Space Launch System, saving money here and there is really important. And, taking the weeks and weeks that it takes to put it on a barge and, send it across the country probably is contributing to the scheduling problems that they've had. They're years behind schedule now. And one piece of that is the need to sort of constantly ship parts across the country rather than sort of sensibly locating the production, testing, and launch facilities all in one part of the United States.
And we are now just around the corner from the first launch of the SpaceX Falcon Heavy. And when that happens, that's going to close the gap between the capabilities of what SpaceX is able to do and what the Space Launch System. The SLS is still going to be able to loft more weight into space, and yet if the Falcon Heavy goes to plan, you're going to be seeing, the three boosters coming back and landing and put back together and stacked up and launched again. It's going to get harder and harder to justify the existence of this program.
Yeah, the largest configurations, the sort of heaviest launch configurations of the Falcon Heavy will be able to launch similar to sort of the lower scale configurations for SLS. So there's a clear capability advantage for SLS, but it's not clear that there's that many tasks that need that kind of capability.
Yeah.
Especially when you think of the fact that SLS is a single launch system. It's going to cost at least $1 billion and perhaps as much as $2 billion to launch it a single time. And sure, you can put more on it than any other rocket, but if you could launch the Falcon Heavy a couple of times and just break your payload in half, then you might get a faster launch. You certainly would get a cheaper launch. And it's not clear that there are that many needs to launch a huge system all at once, kind of Apollo style.
Yeah. I got a bad feeling as this plays out.
It'll be a real blow to NASA SLS sort of loses its mandate, because this is something they've been investing, the better part of a decade in, after investing the better part of a decade in another rocket system, Constellation, that was canceled.
Yeah.
And I think if SLS sort of has the legs kicked out from under it, it's time for NASA to think about whether they need to be in the launch business at all.
Yeah.
Because the landscape just looks so different than it did when SLS was first started. And the rest of the U.S. government, the military, isn't building tanks themselves. They contract out somebody to do that, and it seems like NASA ought to be able to do that for rocket launches as well.
Yeah, I feel like we're one administration away from the program getting reevaluated, but for now, it's it's still going to happen. It's just going to be a bunch of years later. So if all goes well right now, when will we see the first SLS launch? When's the first launch test?
I think it's sometime now in the end of 2018, or it could be into 2019 now.
Right. And first humans in an Orion capsule?
Probably not until the 2020s. If they keep the original schedule, the life support for Orion isn't designed to be finished, I think, until at least 2021.
Right. And 2024, of course, is when the interplanetary transport ship carrying 400 people blasts off on its way to begin the colonization of Mars. So, that is and obviously we say that all props to Musk, but we know that date is going to slip. So, yeah. All right, let's move on. That was awesome. Very interesting information. I really appreciate it. Let's move on. Now I choose in the random wheel of my whims. I want to know about an ancient, or how the river system on Titan is. Sonny Springman.
How is the river system on Titan? So there have been a couple people who've been looking at the similarities between rivers on Titan, which is the largest moon of Saturn, and it is the only moon with a respectable atmosphere. And it has a lot in common with our atmosphere, actually. It has a lot of nitrogen in the atmosphere. And it has, instead of a water cycle like we have here on Earth, with water evaporating, turning into rain and snow, and then raining down, and then forming rivers and lakes and oceans, and then evaporating again, Titan has a methane cycle. So you have methane rain, you have methane clouds, you have methane rivers, you have methane lakes and small seas. So Titan has a lot in common with Earth, except it's much colder. It's a moon, and it has methane liquid everywhere and methane vapor. And then also you get weird things going on with photodissociation of methane into ethane and other weird things. I digress. So a couple of folks from a variety of institutions have been looking at how similar are rivers on Titan to rivers on Earth, and also to the riverbeds that we see on Mars. And their result may surprise you. Neither Mars nor Titan has plate tectonics anytime in the recent past. And so you don't get sort of upheaval as mountains form, changing the course of rivers on Titan or on Mars like you do on Earth. So if you are Team Titan and you think Titan is better than Mars, Titan has so much in common in Mars, because you don't have these tectonic processes changing the course of rivers as things move up and down on the planetary body. Because I can't say planet for Titan. I can call it a world.
Go ahead. Call it a world.
It's a world. It's a respectable world. Like, that's pretty cool. So anyway, we have these three bodies in the solar system where we've seen rivers that have been carved in the landscape, and there are things that are in common, but there's also things that are really different. So I think that's pretty cool.
I'm just moving Titan beside you here, so you can't see it, but Titan is now beside you. So this idea, I mean, we don't see any active like weather happening on Mars, like rain, any hydrological process on Mars
but we
today.
See clouds. There is weather on Mars. It's just not really
right.
There's a carbon dioxide cycle.
Yeah.
Kind of.
Right, but the point is we don't see clouds and rain and rivers and lakes and things, cycling around. And yet, we know we're very experienced with that here on Earth, and we definitely, from the limited observations that we've been able to make of Titan, we see that there. So what did maybe is it that we know more about what the ancient Mars process looked like? Is it that we sort of, what are those features that are very similar?
So we see sort of as flows change on Mars and Titan, I guess that there's sort of more similarity in Mars and Titan that you don't see big changes in topography and how the rivers sort of adjust to deal with that. What you do see on Titan, which I think is kind of cool, is that there might be evidence that tides from Saturn change the thickness of Titan's crust. And so that there might be some more subtle changes there, but you don't have sort of tectonic mountain building processes. So things are a little more flat. So you don't have the landscape being reshaped on Titan or Mars.
I mean, one of the things that's pretty fascinating is, I mean, Titan really does have all of those pieces. It's got the wind flowing that's putting like little tiny waves in the seas. You can even see the dunes across the ocean. And I'm just sort of putting up a picture here, just clearly these river systems. So, I mean, from my unexpert eye, they look similar to Earth, but I guess it's just that it's more of a temporary process, as opposed to like the long-lasting river systems that we have on Earth that kind of grind away at the terrain for long periods of time.
Like on Earth, you have rivers that are sort of fighting against mountains. Mountains get pushed up from tectonics, and so you have rivers that are really battling the topography that they face. Whereas on Titan, you don't really see that. So like on Earth, you might see old riverbeds that might even appear to flow uphill because of how topography has changed since the river formed. But you won't see that on Mars or Titan so much because you just don't have mountain building processes like that.
Yeah.
Right. Like on Mars, pretty much the topography, with the exception of Olympus Mons, was formed during the late heavy bombardment. So asteroids hitting the planet, and that's really what dictates the topography, whereas that's not the case on Earth and not really the case on Titan.
I mean, clearly the plate tectonics have a big impact on what we see here on Earth. Okay. Some cool. Yeah. All right. So let's move on. That's awesome. Let's see. What's next? I guess it's Dr. Kimberly Cartier. I gotta get back into that habit of saying Dr. Kimberly Cartier.
I won't make you do it more than like 5 times.
Like every time, and you will correct me every time I do it wrong. Please do. Let's talk about black hole formation with LIGO.
Yes. So it's been a little bit over a year since LIGO detected the first signal of gravitational waves coming from the merger of 2 black holes. It has since detected at least 1, possibly 2 other signals of gravitational waves. But LIGO can do more than just detect the fact that gravitational waves emerged from black hole mergers. It can also measure the masses of these black holes that were part of this merger, and also the spins of each of the black holes that went into the merger. And for the first detection of the gravitational wave, what was really puzzling to the scientists was that the black holes involved were actually very, very massive. They were 29 and 36 times the mass of the sun, respectively. And that's pretty big for black holes. Certainly not as big as the supermassive black holes at the centers of galaxies like the Milky Way, but certainly bigger than we would expect from a single star just collapsing into a black hole after it dies. So it raises the question of why are these massive intermediate mass black holes the ones that we're detecting causing gravitational waves, and how do those intermediate mass black holes actually form? And a team of scientists have developed a model that they say will allow LIGO to answer that question of how these intermediate mass black holes form. Now, we have a pretty good idea of how the smaller black holes form, things that are a few times the mass of the sun. Those generally form from a large star that reaches the end of its life and collapses downwards into a single black hole. We also have a pretty good idea of how the supermassive black holes form, the kinds that are at the centers of galaxies, from just a bunch of smaller black holes all merging together to make a supermassive black hole that's maybe 1 million times the mass of the sun. But it's the intermediate mass black holes, the kinds that were causing these gravitational waves, that we're not quite sure. They could form either from a collapsing object, like the smaller black holes, or from the aggregation of a bunch of the smaller black holes into a larger one, like the ones at the centers of galaxies do. So it's an open question on how black holes form. And the key piece of information here is that LIGO can also measure the spins of these black holes. And astronomers have been able to create a predictive model that predicts the probabilities of how fast the merged black holes would spin after the merger actually happens. So let's say, for instance, you have a gravitational wave signal that was caused from two black holes, and each of those black holes was the result of a collapse of a single object. So that's scenario one. The resulting spins from that merger would follow a very predictable distribution of spins, where there's a very probable spin state afterwards and very improbable states otherwise. In scenario two, the two black holes that go into those mergers, each of them themselves were the result of a previous merger of smaller black holes, and maybe 2 or 3 mergers previous. And the distribution of spins from the merger scenario looks very, very different from the distribution of spins from the single object scenario. And LIGO, if it detects 100 or so signals from gravitational waves and measures the spins of the black holes that go into that, will be able to distinguish between the merger scenario and the single collapse scenario, which will answer a huge question regarding how these intermediate mass black holes form and how likely it is that these sorts of systems that can cause gravitational waves that we can measure, how frequently those sorts of systems actually form.
Well, we know, as you say, we know how those regular mass black holes form. Supermassive star explodes and you get the stellar mass black hole. And we see these supermassive black holes at the hearts of the galaxies. And I guess one thought was how you could get from one to the other was to find these intermediate mass black holes. And I know astronomers searched in globular clusters as one place for where they might be, but really the evidence for these intermediate black holes has been very surprisingly rare, especially when you see the number of these supermassive ones. I mean, does this help us figure out that connection between the stellar mass black holes and the supermassive ones?
Right. So it definitely does, because if these intermediate mass black holes, these that are a few dozen times the mass of the sun, if they form from the collapse of a single object, like the small ones, they're probably very, very rare, because as far as stars go, the more massive a star is, the more rare the star is. Stars like to form really tiny things really easily, and the more massive you go, the more difficult it is to form those objects. So if these intermediate mass black holes come from 100 solar mass stars that collapse downwards or something like that, they're going to inherently be very rare objects. But instead, if instead the intermediate mass black holes form from individual smaller black holes that all merge together to form a few dozen solar masses, those are probably a lot more common and are more likely to be part of that evolutionary pathway towards building up these supermassive black holes.
Really interesting. Oh, I've got a cool merger video I'm going to put up here for everyone.
Black hole mergers are pretty cool.
Yeah.
Stellar mergers are pretty cool.
All mergers.
All mergers.
And actually, I think this is the one that was detected by LIGO, the video that I'm putting up right now, because one seems to have a bit bigger of an event horizon than the other one.
Yeah, so one's about 36, one's about 29 solar masses.
Yeah, and then you just have one black hole in the end.
Yeah, so essentially, if LIGO can detect 100 or so more gravitational waves in the next few years, we'll be able to measure those spins and be able to figure out how these middle guys form.
Refurio and Acro wants to know how many events has LIGO detected now? Have we gone just beyond the one?
I think there have been 2,
right,
and one that's sort of an iffy maybe scenario, but that's the only ones I've heard of.
And from Ad Filmer, will we need a space-based LIGO type detector to detect these sort of distant gravitational events?
I mean, our ground-based LIGO is doing okay right now. The difficulty with building something like LIGO in space is that you need it to be super stable. And we're having enough troubles getting it super stable on the ground, where things are relatively stationary and we know at least how the Earth is moving and how the sun is moving around the galaxy. We can account for all those motions and try and stabilize things as best as possible. If it were also in space, where we can't control all the, the little factors, if that was also moving, that'd be a lot more difficult, I think,
Right.
to build a LIGO in space.
Very cool. All right, Morgan, we're back around. Let's talk about a Neptune-sized planet that looks a lot like Jupiter.
This is a planet that's called HAT P26b. It's about 437 light years away from Earth. There's a study that just came out about this planet this week. It's a transiting exoplanet about the size of Neptune, very close to its star. It's orbiting, I think, just about 0.04 AU away from its small star. So this is closer to its star than, say, Mercury is to the sun. And because of that, it's quite warm. They're calling it a warm Neptune. It has temperature sort of in the neighborhood of 1,000 degrees. And when you heat up the atmosphere of an exoplanet, you fluff it up. And when you fluff it up, there's more atmosphere blocking starlight, which makes it easier to study the atmosphere of that planet using what we call transmission spectroscopy. And this is when the light from the star passes through the atmosphere and is modified by the molecules and atoms in the planet's atmosphere, and then reaches our telescopes here on Earth. And by comparing that light when the planet is in front of the star and when the planet is not in front of the star, we can work out some of the stuff in the planet's atmosphere. And what's really interesting about this planet is that its atmospheric composition looks a lot more like Jupiter than it does like Neptune. And to measure this, astronomers usually use something called metallicity. And astronomers, being the weird people that we are, call anything heavier than helium, the second lightest element, a metal.
Right.
So you basically add that stuff up and say all of that is metal. And for a planet like Jupiter or Saturn in our solar system, then you compare that metal to the amount of metal in the sun. And planets are generally have more metal than a star does. And so, for example, Jupiter and Saturn have metallicities in the range of, say, sort of under 10. So they're on the order of 10 times more metal per volume in Jupiter or Saturn than there are in the sun. The ice giants, though, Uranus and Neptune, have metallicities much, much higher than that, closer to 100 than to 5 or 10. And so when astronomers measured the metallicity of this exoplanet, they got a value of 4.8. And that is sort of squarely in the range of Jupiter and Saturn, despite the fact that the planet's much smaller, closer in size to Uranus or Neptune. And so the idea here is that the planet must have formed closer into the star than the Neptune did to our sun, because the farther out you get, the more ices, the methane ices, nitrogen ices, things like that you found, because the temperature is cooler, it doesn't melt them away. And so Neptune has a lot of that because it's relatively far away from the star. But HAT P26b has relatively little of that, probably because it formed closer in to its star. But if it had formed sort of at the same time scale as our planets, it ought to then have been more in size of Jupiter. And so they think not only did it probably form a little closer to the star than, say, Neptune did in our solar system, but it probably formed really close to the end of the planet-forming period of the protoplanetary disk. And at that point, other planets that might be in that star system, or maybe were once in that star system, would have used up some of that material, leaving behind less material and concentrating less of these heavier metal elements into the atmosphere of this planet. And so this is sort of just putting in one more shiny object in our box of shiny planets, demonstrating once more that the sort of patterns that we see in our solar system are just that, our solar system. And that when you look out into a galaxy full of planets, we see tremendous variety that we never anticipated.
Yeah, I mean, this is really the lesson that we just keep seeing again and again and again, that is that the universe doesn't match our expectations for what should have been. I mean, these hot Jupiters, planets around pulsars, and as you said, planets that seem to have the wrong levels of metals versus liquids, and this potential migration is a big part. I mean, the thing that I find so interesting is how that gives us hints about what our own sort of original solar system might have looked like. Like maybe there was a lot more migration going on. It would be really interesting to know what the solar system looked like 4.2 billion years ago.
Yeah, there's no way that this exoplanet could have formed where it is today. It's simply too hot to have accreted the amount of material that it did in the location that it did. And we find that over and over and over again for exoplanets. And the sort of simplest explanation for this is the idea that, well, they formed somewhere else and then they moved to their present locations. And that is backed up by some of the observations that we can make in our solar system.
Fantastic. Kimberly, last but not least, let's talk about the discovery of a moon around a large dwarf planet, which still has no name.
It has a designation. It's 2007 OR10.
That is not a
Really
name.
fancy name, isn't it?
But this is the third largest dwarf planet in the solar system, and it has no name.
It's true. Yeah, it's the third largest dwarf planet in the solar system. Only Pluto and Eris are larger than, I'm going to call it OR10, or Oreo. It looks like Oreo. Write it out. I'm going to Oreo.
Or low.
Or Orlo?
Oreo?
Maybe.
Yeah.
Anyway, so a combination of measurements from the Hubble Space Telescope and the Palomar Observatory and the Herschel Space Observatory have confirmed the presence of a moon around the third largest dwarf planet in the solar system, which is OR10 or Oreo or Orlo, whatever we want to call it. And that makes 8 out of 9 dwarf planets that have confirmed moons. The only dwarf planet that we do not think has a moon at the present time is Sedna, but 8 out of 9 dwarf planets now have moons, which is really an interesting thing, since all these dwarf planets are out in the Kuiper belt, and this particular object is about 3 times further than Pluto is, where just the distribution of material in space, it's a lot more sparse. And so the fact that all these dwarf planets, including this one here, has a moon, means that earlier in the solar system, when all these objects were forming, the types of collisions that form moons must have been a lot more common than we expect, because to have 2 objects collide and have the resulting debris form a moon in orbit around the bigger object, the 2 objects have to collide at a speed that's not too fast and not too slow, but it's just right. And the fact that we keep finding moons around these outer solar system bodies means that either the speeds that things were going were, always just right to form a moon, or there were just more collisions than we were expecting, so that the number of times that a moon forming collision happened just is higher than what we thought. And this gives us sort of an idea of how the smaller bits of our solar system were forming, how this might happen in other solar systems, and trying to piece together the history of how all the diverse objects in our solar system actually came to be.
Well, I still can't really give up this concept that the third largest dwarf planet in the solar system doesn't. I'm
going to call it Oreo.
Well, so you're calling it Oreo. Ad Filmer in the chat said Or10, which I kind of like.
Or10.
Yeah. Orton.
Or10. That could work.
Yeah, I think that works really well too.
Orton.
Yeah.
Well, that'll do.
Yeah.
Also, a fun piece of news that the chat in here has just alerted me to is that Voyagian star is currently dipping right now, right this second.
So can you tell me what that means? Right now. What's going on? What does that mean?
So Voyagian star has all these crazy dips that aren't planets but mimic sort of a planet-like signal, and it happens at completely random intervals. And Kepler detected quite a few of them, and then it just stopped dipping, these random dip events. And so Tabitha Voyagian set up a crowdfunded monitoring program to monitor Voyage star to catch it the next time it does one of these unpredictable dips, so that every telescope that can swing over and catch this strange eclipse-like event while it's happening in as many wavelengths as possible to try and figure out what kind of material could be blocking the starlight. So the monitoring program has paid off. If you contributed to that Kickstarter campaign last year, it has paid off because it's dipping right now, and there are quite a few telescopes that are observing it as we speak.
So there you go. We talked about crowdfunding science research.
It worked.
It worked. We experienced it.
It's doing it right now, and this is I think it's about 2 or 3% of the starlight is being obscured, which makes it one of the bigger eclipse events that we've observed around Voyage and Star. So I'm going to really look forward to the next week of getting to see all of the fun analyses that happen from these observations.
Well, that's great. Well, as soon as you know whether it's like a Dyson swarm or a Dyson ring or a Dyson sphere, please let us know.
Yeah, I'm personally a fan of the star just ate a planet and now it's digesting scenario.
That's pretty cool.
That's my personal favorite.
Yeah, that's exciting.
So that's breaking news, and maybe next week we'll have some more updates on that.
All right, so we've reached the end of our hour. I'd love to, we need to sort of wrap this up, move things along. But Kimberly, you're still on my screen right now. So where can people find out more?
So people can find out more by following me on Twitter, as always, at AstroKimCartier, and by going to my website, KimberlyCartier.org.
Fantastic. And once again, congratulations on reaching your doctorate.
Thank you. It's possible.
Yeah. And so now
it happens.
your dreams can become real. Fantastic.
Yeah.
All right. Sandy Springman, where do people find out more?
Sandy on Twitter, SONDY, and Sandy.com.
Yeah, you got
updated a while ago.
All the Sandies.
Except on Instagram. Some punk has Sandy on Instagram.
Are they active?
I got Sandy on Twitter because I knew someone at Twitter. But
Morgan Renberg, where do people find out more?
Well, I know no one at Twitter, but you can follow me at Morgan Renberg. You can visit my website, morganrenberg.com. And if you want to check out more about that interesting warm Neptune, you can check out the video that I wrote for SciShow Space that should be going up this afternoon.
And now that you're a doctorate, what's going to happen in the next little while?
Yeah, so I will be moving in just about a month down to the great state of Texas to join the staff of the Fort Worth Museum of Science and History, where I'll be overseeing the planetarium, developing some cool content for virtual reality, and I hope a whole lot more.
Wonderful. Well, as soon as I can nag the fans to participate in everything you're working on, let me know.
And yeah, send me your mailing address when you get a new one, Morgan.
I'll do my best.
All right, I'm going to put us back in that mode. I'm going to put us as the guest. All right, well, thanks everyone for joining us this week's Weekly Space Hangout. So great to have the crew back. Once again, thanks to all the fans. Thanks to our guest. And thanks to the panelists. And we will see you all next week. Bye.
Wait, it's a holiday next weekend. Are we going to do this?
I don't know. Probably. It's in the schedule. I believe so.
Okay.
Maybe not a holiday here. Maybe it is a holiday.
Not a holiday
here.
in Canuckistan.
Yeah. We have our May long weekend. We'll just be gardening. It'll be fine. Yeah. But thank you for being so cognizant of my sort of Canadian holiday. Aw. All right.
Yeah, Fraser, you're gonna have to give me tips for visiting BC.
I will. All right. We'll see you all next week.
Take it easy.